Energy from chemicals. Changes in energy during a chemical reaction occurs as forms of energy are changeable. Exothermic reaction. An exothermic reaction is a reaction in which heat energy is given out, exit, to the surrounding temperature increases in this case. New bonds are formed within the product, which requires less energy. When heat is given out, the solution becomes warm, and later the temperature goes back to room temperature. Example. For instance, dissolving sodium hydroxide or any anhydrous salt in its aqueous solution will emit heat energy. When acid and alkali react together, they give off heat to form water, and the process is known as neutralization. All combustion reactions emit heat energy, hence are exothermic reactions. Also, whenever there is a change of state such as in respiration or condensation, when gas changes into water or vice versa, heat is emitted. Moreover, exothermic reactions include when metal is displaced, magnesium reacting with copper 2 sulfate, such as in rusting of iron or corrosion. Endothermic reaction. An endothermic reaction is a reaction in which heat is absorbed from the surrounding. Temperature decreases in this case. When heat is absorbed from the surrounding of the reactants, the solution becomes cooler, and later the temperature goes back to room temperature. Example. For instance, light energy from the sun is absorbed by the plants during photosynthesis to produce glucose. Compounds take in heat energy to decompose, known as thermal decomposition. Evaporation and melting of compounds require heat energy to be absorbed to break the bond and change the state of the compound. Also, some ionic compounds, example, ammonium chloride, potassium chloride, and hydrated copper, 2 sulfate, absorb heat energy to dissolve in water. Moreover, when acid and bicarbonates react together, they absorb heat energy to form a salt. Enthalpy change in a reaction. The amount of energy involved in a reaction is known as the heat change or enthalpy change of the reaction. Enthalpy change is an amount of difference in energy of the reactant and product. Symbol, increment H. Increment is Greek letter delta, which means change, and H represent heat content stored in substance. Unit AKJ, kilojoule. Formula, increment H equals total energy of product total energy of reactants. Bond breaking and bond making. Bond breaking and bond making causes energy change because bonds of reactant first need to be broken, then new bonds will form as a product. Energy is absorbed in bond breaking, so bond breaking is an endothermic process. Energy is released in the bond making, so bond making is an exothermic reaction. Overall enthalpy change in terms of bond breaking and bond making. Enthalpy change, increment H, equals total energy absorbed for bond breaking, total energy released for bond making. Increment H equals bond breaking energy, bond making energy. How can we suggest that a reaction is exothermic or endothermic? Total energy absorbed for bond breaking is less than the total energy released for bond making in an exothermic reaction. Total energy absorbed for bond breaking, total energy released for bond making. Total energy absorbed for bond breaking is greater than the total energy released for bond making, making an endothermic reaction. Total energy absorbed for bond breaking, total energy released for bond making. Example. Find the value of increment H for the reaction between hydrogen and oxygen. Calculate whether the reaction is exothermic or endothermic. Bond, energy kJ/mol. HH, 436. OH, 464. O equals O, 497. Solution. Equation. 2H2 plus O2 2H2O. 2, HH, plus O equals O, 2, HOH. 2, 436, plus 497, 2, 464 asterisk 2. 1369 1856. Increment H equals bond breaking energy, bond making energy. Increment H equals 1369, 1856. Increment H equals 487 kJ/mol. Enthalpy change is negative, which means the reaction is exothermic. Activation energy EA. Activation energy is the minimum amount of energy required to proceed with the chemical reaction. It is denoted by EA. Energy profile diagram, it indicates the changes in energy during a chemical reaction. The difference in energy of products and reactants shows the enthalpy changes of reaction. Reactants having less energy than the activation energy do not form products as their bonds cannot be broken. However, particles with more abundant energy form new bonds on collision. Combustion of fuels. Fuel is a source of energy that is used up daily in an enormous way. Fuels are the substance that can burn quickly in the air to give out energy. Wood, coal, petroleum, hydrogen, and natural gas are an example of fuels. The most commonly used fuels are called fossil fuels such as coal, petroleum, and natural gas. What happens when fuels burn? Coal is primarily made of carbon, and it gives off carbon dioxide when burned in excess air. Heat energy is also produced. Carbon plus oxygen, carbon dioxide plus heat energy. Most fuels comprise of carbon and hydrogen. Methane plus oxygen, carbon dioxide plus water vapor plus heat energy. CH4, G, plus 2O2, G, CO2, G, plus 2H2O, G, plus heat energy. The above equations represent the complete combustions of fuel. Incomplete combustion. Incomplete combustion refers to using a limited supply of air to ignite the carbon particles and give off carbon monoxide gas, which is also poisonous. Methane plus oxygen, carbon monoxide plus water plus carbon plus heat energy. For CH4, G, plus 5O2, G, 2CO, G, plus 8H2O, G, plus 2C, S, plus heat energy. All combustion reactions are exothermic reactions because they release heat energy. Fuel cells. A fuel cell refers to a chemical cell in which reactants are used to generate electricity. For instance, the hydrogen-oxygen fuel cell is used in space vehicles. Hydrogen-oxygen fuel cell. In the hydrogen-oxygen fuel cell, hydrogen is used as a fuel. The combustion of hydrogen is produced by water and heat energy. Hydrogen plus oxygen water increment H equals minus 484 kJ. 2H2, G, plus O2, G, H2O, G, increment H equals minus 484 kJ. Electrical energy is produced in this reaction. Hydrogen can be formed by either electrolysis or cracking of hydrocarbons. 1. Any hydrocarbons when reacts with steam over a nickel catalyst, and its byproducts are CO and hydrogen. However, carbon monoxide CO is again reacted with more steam to generate CO2 and hydrogen gas. 2. Electrolysis of water can also generate hydrogen and oxygen gas. However, it is limited due to cost. Hydrogen, which is formed, is further reacted with O2 to generate steam and heat energy, which moves the vehicle forwards in engines. The figure below shows the reaction that takes place in a hydrogen-oxygen fuel cell. A fuel cell transforms chemical energy into electrical energy. Advantages of using hydrogen fuel cell. 1. Renewable source of energy. It is used as a rocket fuel as well. 2. It does not cause pollution and burns cleanly in the air. It produces steam as a byproduct of the reaction. 3. Efficient source of energy as it provides twice as much energy if 1 gram of hydrogen is burnt in air. 4. Efficient conversion of chemical energy into electrical energy. Disadvantages of using hydrogen fuel cell. 1. Hydrogen is flammable and explosive. 2. Hydrogen is very light. 3. Hydrogen is costly. Natural gas and petroleum. Petroleum and natural gas are fossil fuels, and they both are used as a source of energy. Petroleum. Petroleum is a naturally occurring mixture of hydrocarbons, primarily alkanes. Natural gas. Natural gas typically consists of 70–90% of methane and short-chain alkanes such as ethane, which is approximately 0–20%, propane, and butane. Fractional distillation of petroleum. Petroleum must be refined or separated into fractions prior to using it. It can be made beneficial by performing fractional distillation. Each petroleum fraction is a mixture of hydrocarbons which boils over a specific temperature range. A lighter fraction consists of smaller hydrocarbons, whereas the heavier fraction consists of more significant hydrocarbons. Uses of petroleum fraction. Petroleum gas. Petroleum gas is C1 to C4, boiling point is 40 OC, and it is used for cooking and heating purpose. Petrol, gasoline. Petrol is C5 to C10, its boiling point is between 40 to 75 OC, and it is used as fuel for motorcars. Naphtha. Naphtha is C7 to C14, its boiling point is between 90 to 150 OC, and it is used as a raw material for manufacturing petrochemicals such as plastics and detergents. Kerosene, paraffin. Kerosene is C9 to C16, its boiling point is between 150 to 240 OC, and it is used as a fuel for aircraft engines, cooking using oil stoves, and heating. Diesel oil. Diesel oil is C15 to C25, its boiling point is between 220 to 250 OC, and it is used as a fuel for diesel engines, in buses, lorries, and trains. Lubricating oil. Lubricating oil is C20 to C35. Its boiling point is between 300 to 350 OC, and it is used for lubricating machines for making waxes and polishes. Bitumen. Bitumen is greater than C70, its boiling point is greater than 350 OC, and it is used for making road surfaces and roofing. Photosynthesis. Photosynthesis can be considered as the inverse of respiration, as energy is absorbed from the sun, hence being an endothermic process and used to build up simple sugars like glucose. Carbon dioxide plus water vapor, glucose sugar plus oxygen. Plants use glucose as a form of energy, and according to scientists, it can be used as a combustible fuel. Glucose can be fermented using yeast to form ethanol. Ethanol is further heated to its boiling point, that is 78 degrees Celsius, by fractional distillation, and the water is removed. The resulting ethanol is mixed with fuel to generate energy referred to as biofuel, which is a renewable source of energy.